Okay, so in the last couple of videos, we found out that you can compute the GCD of two numbers a and b by noticing that this is actually, the GCD is actually equal to the GCD of, oh, I didn't want to move that one. There we go. The GCD of a and b minus some multiple of a. This is for k in the positive integers. Actually, sorry, just k in the integers. The next thing I was going to say was that k doesn't have to be positive, so we don't have to be subtracting. In the case of the ones we were doing, right, we would have like b is bigger than a. So if we did like the GCD of, I don't know, 72, and I don't know, let's say 15, this would be the same as the GCD of 72 minus 4 times 15. So we would be subtracting a multiple of the smaller number while keeping everything positive. That was just for the purpose of coming up with the GCD, which was the positive number, which is the largest positive number, which divides both of them. And then this would be the GCD of 12 and 15, and then we'd subtract 12 from 15. This would be GCD of 12 and 3, and this is, of course, equal to 3. I'm just going to skip the rest of these steps because that's not the point of this. This is just sort of remember what we were doing. It's actually true that, so k, since k can be any integer here, it's actually true that we can write this as, maybe I'll just rewrite this entire thing. The GCD of a and b is equal to the GCD of a and b plus k times a for any k in the integers. So this could be a negative thing that we're adding here. K times a could be negative, k times a could be positive. Generally, we assume that a and b are positive integers, but we could do this whole thing with negative integers and then multiply by a -1 at the end. It doesn't matter at all. The idea is that the GCD of a and b is the same as the GCD of a and b plus or minus any integer multiple of a. This was why this worked. So we're going to prove this now. And I very often like to do examples of how to use stuff before we prove them, because if you just kind of prove it, it can be a little bit confusing and people sort of disengage and their brains hurt. Once you've seen it working, now we can start to think about, okay, and also seeing it working very often helps you understand the proof. We can think, okay, why did it work? And then we're going to use this. We're going to use this as our segue into the extended Euclidean algorithm, which is what they usually show you first. And I think that's a terrible idea generally, teaching-wise. We're going to use that to segue into the extended Euclidean algorithm and how to use it to find modular inverses. That's what we're kind of building up to. Okay, so how do we prove this? Well, the proof of this thing, that GCD of a and b is the same as the GCD of a and b plus k times a. What we're actually going to show is that all of the common divisors, the set of common divisors of, so the set of common divisors of a and b, and this is a set, we're going to show that this is the same as the set of common divisors. Actually, I'll just copy this. I don't want to write it out again. Is the same as the set of common divisors of a and b plus k times a. b plus k times a. So what we're going to do is and this is going to be a sort of two-part proof. First, we're going to show that if a number divides a and b, if a positive integer divides a and b, excuse me, then it will divide b plus k times a as well as a. And then we'll show the other way. If it divides a and b plus k times a, then it will divide b and a. And so when we find out that the set of common divisors of a and b is the same as the common divisors of a and b plus k times a, well, then the greatest common divisor is just the largest element of this set, which is the same as the largest element of that set, because they're the same set. So let's start by assuming that d divides a and d divides b. So that means that d is a common divisor. D is a common divisor of a and b. So what does that mean? That means that a is equal to d times, say, q, and b is equal to d times, I don't want to use p because usually we say p for primes. We'll call it d times m for q and m are in the integers. And this is just what divisibility is, right? If d divides a, that means that that A is an integer multiple of D. If it divides B, then it means that B is an integer multiple of D. So then let's think about, so now we want to show that D now will divide A and also B plus K times A. Well, if D divides A, then D divides A. That's just given. We get that for free. But what about B plus K times A? We want to show that D divides this thing. But B is D times M. So this is D times M plus, this is supposed to be the beginning of a K. There we go, plus K times, and this is that's the B. A was D times Q, right? D is a divisor of A, so A is D times Q. So this is K times D times Q. That's the A here. This is the B here. And then, of course, we can factor out a D from this. This is D times M plus K times Q. So this means that D divides A plus, or A, and also D divides B plus K times A. So actually, this is one we just proved. I don't really need to write this one again. This shows that D divides B plus K times A. So what's that saying? That's saying that the common divisors of A, B is a subset of the set of common divisors of A and B plus K times A, right? If D is in here, so D is in this set, D is a common divisor of A and B, then it's a common divisor of A and B plus K times A. And now we just show the other, what we call the opposite inclusion. So we say if D divides A and D divides B plus K times A, so it's in the purple set up there, it's a common divisor of A and B plus K times A. Now we want to show that it divides A and B, so that it's a common divisor of A and B. And that will show that these sets are equal. That will show that the common divisors of A and B plus K times A are the same as the common divisors of A and B, and therefore that the GCD, the greatest element of each of these sets, is the same. And that will prove it. And that will justify what we did here. That will show why this process worked. And then it's going to lead us into why the Euclidean algorithm works, why the extended Euclidean algorithm works. Okay, so again, so we're trying to show that D divides A and B. We have D divides A. Let's just show that D divides B. How are we going to do that? Well, again, if D divides A, then A is equal to D times Q. If D divides B plus K times A, then B plus K times A is D times M. And this is again for some Q and M. And I'm sort of abusing notation here. This is I'm just not picking new letters. This does not have to be the same Q and M as in here. This is for some. We would say there exists M and Q in the integers such that this happens. And these are sort of self-contained. These are separate. This is not the same Q and M in there. I'll just put this because I can't stress this enough. These are not the same. These are different Q's and M's. I'm just not picking new letters because there's not really much point. Okay, so A is D times Q. B plus K times A is D times M. And so then what can we do with this? Well, let's transplant the A in there. There's an A in here. B plus K times A, we have B plus K times A is equal to, actually let's start the other way, just to be sort of really circumspect about this. D times M is B plus K times A, and K times A is this D times Q. So we have D times M is B plus K times D times Q. And then what can we do? You guessed it, we can isolate B. We can subtract the dq from both sides. B is D times M minus D times Q, and we factor out the D. It's D times M minus Q. B is equal to D times M minus Q. That means that D divides B. So D divides B. So that means that D is a common divisor. D is a common divisor of A and B. We just showed, and this is, I'll change this from orange to officially green now. We just showed the opposite inclusion, that the common divisors of A and B are the common divisors of A and B plus K times A. So if the set of common divisors of A and B and the set of common divisors of A and B plus K times A are the same, then their greatest elements are the same. And that's why That's why this works. So this is true. The GCD of A and B is the same as, and there's nothing special about adding multiples of A to B. You could prove the proof just with the roles of A and B reversed and show that this is equal to, it's actually equal to the GCD of A, B, and, of B, and let's say A plus K times B, right? You can just add multiples of integer multiples of one of them to the other one and not change the GCD. The GCD will always be the same. And that's why we can do stuff like this, where we take two numbers and we're trying to find a positive, right? Get the positive GCD. Because if you did this and you weren't trying to keep them positive, you could wind up with a negative number. Then you just multiply it by a -1 to get your positive GCD, because the definition strictly is that it's supposed to be positive. But this is why we can take two numbers and just subtract the smaller one from the larger one, or subtract the largest multiple of the smaller one that we can come up with from the larger one, reducing the larger one mod the smaller one, so replacing the larger one with its remainder when you divide by the smaller one, because that's just subtracting a multiple from it. Right? That is why we can do this. That is the key to this. That's why this works. And we're going to see in the next video that this principle, right, of having the GCD of two numbers is the same as the GCD of two other numbers, and then you get smaller numbers that have the same GCD, and then you do that repeatedly. That's the idea behind the Euclidean algorithm, which then we can use. And again, in practice, we're not going to do that one. We'll just do this one because it's quicker. But then if we need to find modular inverses, we need to use the extended Euclidean algorithm to actually compute the modular inverses, and then we need all the steps. We have to. This one won't work for that. We're going to need that for this. So that's going to be the next thing we do. And we're going to understand what we're doing and why it works, which is how we can use it accurately and efficiently and actually understand it and level up and become really, really good at this by taking the time to understand the mechanics behind it. So that's going to be in the next video, modular inverses.